Before finding the values of A and B, coefficients A and B with respect to the initial displacement, we will first analyze the nature of the solution uh, which we have got from this equation. So we will just rewrite the equations a bit. First thing, we'll take the e to power minus c by 2m common outside, and then we will get a e to power square root of c by 2m whole square minus k by m multiplied by t plus b e to power square root of c by 2m minus c by 2m whole square minus k by m, this whole thing multiplied by t. So same values but with positive and negative signs for b, a and b. So what is the nature of the solution? This term is since c is positive, the damping is positive, then damping cannot be negative because f damping is equal to cx dash. So c is positive, so this term is exponentially decaying term, as both c and m both are positive. So e to power minus c by 2m is an exponentially decaying term. This will add damping to the solution, damping to amplitude. So A and B, as you saw in the case of free vibration, A and B come as the amplitude of the solution, and the amplitude of the solution is multiplied with a exponentially decaying term. So this term will create damping to amplitude, damping to amplitude, and amplitude. This means that amplitude will decrease with time. So this is what we expect in the case of damped oscillation. Now, what is the nature of exact solution that we have? For that, we have to analyze the quantity within the brackets. So now the nature of e to power this quantity, that is c by 2m whole square minus k by m, that will depend on whether c by 2m whole square is greater than k by m, smaller than k by m, or equal to k by m. So if c by 2m whole square is greater than k by m, then c by 2m whole square minus k by m is positive, and the quantity that you are getting here inside the bracket x equal to e to the power minus c by 2m multiplied by a e to the power, you'll get a positive quantity multiplied by t plus b in e to the power a negative quantity multiplied by t. So both of these are a both of these are a simple exponential functions. So this is exponentially growing function e to the power positive t, and this is exponentially decaying function. And since this positive value here, which is exponentially growing function, is c by 2m whole square minus k by m square root, this thing will be always less than c by 2m. So when because c by 2m whole square root is c by m, and this quantity, if you just take square root, you will see m, you are subtracting something out of that, and then you are taking the square root. So absolute value of this quantity will be less than absolute value of c by 2m. So hence, when you will multiply this expression e exponential minus c by 2m with this positive quantity, you will get basically e to power minus c by 2m plus square root of c by 2m minus k by m, c by 2m whole square. This quantity here, what we see here, s1, will be negative because c by 2m is greater than c by 2m whole square is greater than k by m. So this quantity is positive. Taking square root is possible, but whatever this value is, that it will be less than c by 2m. So net effect will be negative. So s1 will be negative. So here in this case, when C by 2m greater than km square, you get both quantities x, both quantities S1 and S2 as negative. So in this case, both S1 and S2 are negative. So the solution is simply an exponentially decaying solution. So there are no oscillations. Decaying solution. So if you plot it on the graph, it will look something like this. X against time. There will be no oscillations. So this case is called over damped case when C by 2m square is greater than K by m. So in this case, the value of C is too high to allow any oscillation. If you pull the spring and you have an initial displacement x, when you are and you have the dashpot attached to the system, so when you are just releasing this mass, it will just slowly come back to its original equilibrium position like this in an exponential fashion. There will be no oscillation here. This is case 1. Now the second case is when C by 2m whole square is equal to K by m. So in that case, what will be the nature of S1? S1 is minus C by 2m plus square root of C by 2m whole square minus K by m. So this quantity will become 0 in this case where C by 2m whole square is equal to K by m. So you will get S1 is equal to S2 is equal to minus C by 2m. So in this case also you can see both S1 and S2 are real and negative. So here also only an exponentially decaying function. So the second case is called a critically damped case. So this case is called case of critical damping. So here the solution inside the square root that you see for both the roots, it becomes 0. So below this value of C by 2m whole square, the expression inside the square root will become negative, and then we will start to get oscillation, because square root of negative value will be a iota function, and a iota function can be decomposed into sine and cos wave that we will show you next in the third case. But this is the case where up to this value, up to this damping, the oscillations are not present. So the function of x, the displacement, is a pure exponentially decaying function. So you have e to power minus e to power s1t. So s1 is c by 2m t, and b e to power minus c by 2m t. So both of these are exponentially decaying function. So if you plot your displacement against time, it will be an exponentially decaying function. There will be no oscillations present. No oscillations. So it is a lowermost value of the damping up to which the oscillations are not present. Below this value, if the damping is below this value, then oscillation will start to appear. Is below critical damping, then oscillations will appear. Oscillations will appear. That we will see in the third case. So that's why I wrote down the observations clearly here again. So below the critical damping, oscillation will appear, and above or equal the critical damping, the displacement will be an exponentially decaying function. That's why this is an interesting topic that you should consider in the damped systems, that what is the damping ratio. So we will determine the critical damping constant, that is C. Damping is purely defined by C. So let's say the critical damp. Let's say we term it C subscript small c, that is critical damping Cc. That will be equal to Cc by 2m whole square equal to K by M. It will be given by this identity. So if you solve this equation, you will get Cc whole square equal to 4m square K by M square will get cancelled out. So critical damping will be 2 square root of Km. So this is the critical damping constant. The damping is defined by a damping constant where F is equal to Cx dash. So this is a damping constant which if it is above the critical damping or equal to critical damping, the critical damping is below the critical damping, then the oscillations will appear. This helps us to define a non-dimensionalized damping. So the actual damping will vary from case to case, but you can have a non-dimensionalized factor which can help you to see whether the system is critically damped or it is over damped or under damped or critically damped. So non-dimensional damping is defined as Z, function as Z is equal to C by Cc. So C is damping constant and Cc is the critical damping constant. The critical damping constant you can get from the parameters that it is equal to square root of K, stiffness of the system and mass of the system. And for underdamped, the damping will be less than the critical value. So Z will be less than 1. Overdamped, that we saw in the case 1, the first case. So Z will be greater than 1. The damping is excessive, there is no oscillation, just the exponential decay. And critically damped, that is also exponential decay, there is no oscillation. There you get Z is equal to 1. So if you see the oscillations for critical damping case, so what is the equation for motion for a critically damped case? That you have seen that x equal to a e to power minus c by 2 m t plus b e to power minus c by 2 m t. Here if you just take the c by 2 m t common outside, you will get a plus b. So the number of constant will reduce to 1 if e to power minus c by 2 m t is taken common outside. So that is not possible because then you have two initial conditions and like x0 and x dash 0, two initial conditions are there. So you need to have two constants. So if you go to your mathematics fundamentals, you will see that in such cases the constants are given as a plus bt. You have a t extra, and then you can take the e to power minus 3 by 2m t outside. So this is the equation for critically damped case. The details for this mathematical identity you can see in your mathematics textbook. Damped case. This special case comes when the both of the expression functions that we have assumed, y is equal to f1x, a f1x and b f2x, and in case f1x is equal to f2x, then you have identity that y is equal to a plus bx f1x, because f1x is equal to f2x. So it's the same coordinate identity we have used here. So we found the equation for the critical damped case. How the motion look like? So if you substitute the initial condition, you will see that the motion depends on the initial condition. So let's say this is the initial displacement x0, initial displacement, and you have a initial velocity x dash 0. Those are your initial conditions from which you determine the equation of motion even for the free vibration. This is initial velocity. So if x dash 0 is greater than 0, there is some initial velocity, then it will look like this. The graph will go towards top and then it will come and go logarithmic decrement and it will tend to 0. If x dash is 0, there is no initial velocity, then it will just exponentially decay. So this is the case for x dash initial velocity is equal to 0. And third interesting case comes when the x dash is negative. So you have the initial velocity. That initial velocity will cause the line to overshoot the mean equilibrium line. It will overshoot and then it will come back to its mean position. That is displacement x is equal to 0. So this is for the case x dash 0 is negative velocity. It will start moving towards the equilibrium position, it will overshoot the equilibrium position, then it will return back. So these are the graphs for the critically damped case. Now we will move on to the case 3, that is of interest for the damped oscillation, where you really see the oscillation. In this case, c by 2m whole square is less than k by m. So the factor inside the square root that you see c by 2m whole square minus k by m, this becomes negative. So this becomes 0. So this expression is negative. So square root of negative quantities, you know that it becomes a complex function, because square root of minus 1 is iota. I is a complex number, not a real number. So how the equation of motion will look like? The equation of motion was a e to power minus c by 2m plus square root of c by 2m whole square minus k by m. This was the first root, and the second root was b e to power minus c by 2m minus c by 2m whole square k by m multiplied by t. So in this case, both of these things are negative. So we will take an absolute value of this expression c by 2m whole square minus k by m, and we will take minus c by 2m common outside. We will get e to power minus c by 2m taken outside common, a iota, because this value, this c by 2m square by is negative. So you get square root of minus 1 iota outside, and then you can take the absolute value of c by 2m whole square minus k by m. Absolute value will be a positive quantity. You can take the square root of that. T plus b e to power minus iota, here you have minus, see, and you get the same quantity, absolute value of c by 2m whole square minus k by m, the absolute value of that multiplied by t. So this is the equation for the underdamped case. Now we will analyze this function and see how the oscillations will appear. We will plot them graphically. So for doing that, we have to first simplify this expression inside the root. It looks too complicated to analyze at present. So we'll take this expression c by 2m whole square minus k by m. Now we will represent this function in terms of critical damping and the damping constant, the damping ratio. Critical damping is Cc and damping ratio is V, that is equal to C by Cc, that is real damping divided by critical damping. This is negative in the underdamped case, that is the present case, the case 3 underdamped, where C by 2m whole square is less than K by m is underdamped. So in the present case, V is equal to is less than 1, V is equal to C by Cc, and Cc critical damping is equal to 2 square root of Km. So the damping will be equal to V into Cc, that is equal to V 2V square root of Km. So this value, if you substitute in this expression, you see that you will get 2V square root of Km divided by 2m whole square minus k by m. So here the 2 and 2 get cancelled out, and square root of m and just the m, you will get square root of m in the denominator. You will get z
square root of k by m whole square minus k by m. Square root of k by m whole square become k by m, and k by m if take common outside, we get square root of k by m common outside, and we get square root of g square minus 1. So absolute value of we are evaluating the absolute value of this function. So absolute value of g square minus 1. So absolute value of g square minus 1, because since g is less than 1, so absolute value of g square minus 1 will be equal to 1 minus g square. G square is less than 1. We have taken this value to avoid further confusion. So we get the quantity in the square bracket as equal to square root k by m multiplied by root over 1 minus g square. So I've written the key observation from the third case here. Under damped case, t by 2m whole square is less than k by m. And this expression inside the square root, if you simplify, it comes as a multiplication of square root of k by m multiplied by the damping ratio. Zeta is z is the damping ratio. Since g is less than 1 for this case. Now, if you see this expression to square root of k by m, if you recall the natural frequency expression for the undamped oscillation, or pre-vibration or undamped oscillation, the natural frequency omega natural was square root of k by m. So this value again you can substitute here. This expression inside the square root becomes omega n multiplied by square root of 1 minus g square. So this value if you substitute in our equation of motion, let's see what we get. We'll get x is equal to e to power minus c by 2mt multiplied by a e to power iota omega n 1 minus g square t plus b e to power minus iota omega n 1 minus g square t. Now 1 minus g square is the positive value. So this will be some positive value, this will be some positive value. So you have some constant, let's say k. So omega n 1 minus g square, for simplicity, it is some, will not use k because that is a stiffness. We'll let's say used omega d. So that is also a significance associated with this relation omega n 1 minus zeta square square root equal to omega d. That I will explain now. That this omega n is the natural frequency of free oscillation and z is the damping ratio. So if you substitute in this relation, we will get e to power minus c by 2mt, then square root of a e to power I omega dt plus b e to power minus I omega dt. Now, exponential function can be written as a combination of cos wave and the sine wave. If you recall your theory of complex number, you'll see that e to power ix can be written as cos x plus I sin x. So this x is not our displacement, this is some general x. So this is you get from the theory of complex numbers. So if we substitute this value here, what we will get? E to power minus c by 2mt a cos omega t plus I sin omega t is equal to multiplied by a plus b minus, here the x function is minus omega dt. The cos minus is cos only. So cos omega t, omega d everywhere, omega dt, and minus sine minus theta. Sine minus theta is minus sine theta. You get minus sine omega dt. So hence you can see here that the displacement is a function of cos and sine function. So hence the motion is oscillatory. oscillatory motion. So in underdamped case, you get oscillatory motion because you get cosine and sine functions against the time period t. So we'll just rearrange to get our final equation, and here again we will use some more simplification of for c by 2mt here, because we have expressed everything in non-dimensionalized quantities, omega d, omega and omega as v. So we'll write c by 2m also. So c, as you know, it is equal to v into critical damping, cc. So critical damping is the square root of 2 km, 2 multiplied square root of km into v by 2m. 2 and 2 get cancelled out, and you'll get v square root of k by m, and k by m is the omega natural frequency of undamped oscillation. So you will get c by 2m equal to v into omega. So this thing also will substitute, and we will get final expression for x, that x equal to e to power minus v omega t plus a plus b cos omega d t plus iota a minus b sine omega d t. So we'll write our pre-learnings here, the equation for the motion in terms of the cos and sine function, and c by 2m is v omega that we saw, and omega is undamped natural frequency of system, that is equal to square root of k by m, and v is equal to damping constant divided by critical damping, that is called damping ratio, and it is less than 1 for the underdamped case that we are considering here. So now if you analyze this function, you have a x displacement that is oscillatory in time, a plus b being some constant and a minus b some other constant that will be determined from initial conditions. So let's say a plus b is a1 and a minus b is a2. So the equation is a1 cos omega dt plus a2 sine omega dt. A2 being iota a2 a minus b, that we have treated as a single constant, sine omega dt. So this is just the expression inside the bracket is similar to solution for free vibration, the undamped case. So this is just a oscillatory function, and the expression here is similar to critically damped case. Critically damped case, the equation of motion was a plus vt e to power minus c by 2mt. So c by 2m is nothing but z into omega. So it looks like similar to the critically damped case. So here you have a multiplication of damping and oscillation. So a combination of damping and oscillation. This you get in the underdamped case. So in this case, the oscillations will occur, but they will be damped over a period of time, and they will be zero. So you have amplitude factor here. So the amplitude of oscillation, the oscillations will occur, but the amplitude of oscillation will decay with time due to the exponentially decaying function that you have present here. So if you get multiplied with increasing time, it will get multiplied with the amplitude, and it will keep reducing the value of the amplitude. The amplitude of oscillation is decaying time. So these are called damped oscillation in practice. So in the earlier two cases, overdamped and underdamped, you get no oscillation, just the straight function like this or like this, but it just reduces. But in the underdamped case, you get oscillation, the amplitude of which will decay with time. So now we come to an interesting observation, that what is the frequency of undamped oscillation. So if you compare this expression in the bracket here, that is similar to the solution of free vibration. So this expression is something similar to free vibration. So pre-vibration we had A cos omega t and B sin omega t, sin omega t. So comparing with that, you get the frequency of oscillations for a damped case, under damped case. So the frequency of damped oscillation is equal to omega d. That you can see by comparing with the original equation. It's something similar to the pre-vibration. So there it was omega, the natural frequency. Here it is omega d, the damped frequency, omega d. So omega d is the damped oscillation frequency, and what is its magnitude? We saw that omega d is equal to omega multiplied by 1 minus v square. So omega is the natural frequency of the system that you can get by the square root of k by m, and v is damping ratio that you get by c by cc, critical damping, and critical damping is equal to 2 root over k by m. So these are some of the key formulas that you should remember, because the simple objective question can be formed from these formulas. You should remember the natural frequency is square root of k by m, the critical damping 2 multiplied by square root of k n multiplied by m, v the damping factor, that is damping ratio, is equal to actual damping divided by actual damping. And for underdamped case, the oscillations will occur, and for the underdamped case, the damped oscillation frequency is equal to omega multiplied by 1 minus v square.